So last time we got ourselves pretty close to the Zelevinksy classification. We got ourselves basically set up to drop it today. So let me briefly review some things. We have these things called segments. They are collections of complex numbers. So segments we denote with delta, possibly delta some subscript. We use interval notation to say the complex number that it starts at, the complex number that it ends at. And it's always just successive complex numbers, right? So the segment written as delta AB, maybe bad notation because I'm using little a's for multi-segments, but this is the ordered set A plus 1 up to B. And we also considered things called multi-segments. So a multi-segment was just a multi-set containing segments. So that just means, like in this example here, we can have multiple copies. To each segment, it turns out to each individual segment, we can associate an induced representation where the numbers appearing in the segment tell us exactly the twists of our just usual p-adic norm character that we're going to take, or we take that p-adic norm character, we put it to the exponent of whatever these numbers are here, tensor those all together, we get an induced representation. That induced representation has both a unique irreducible quotient, which we denoted by Q delta, and a unique irreducible sub, which was denoted by Z delta. We then repeated this process with these new representations that we get. So if I had a multi-segment that contained delta 1 up to delta R, then after obtaining those subs or quotients, what have you, I then go and I place all of these subs, Z delta 1 tensor product up to Z delta R, where of course this external tensor product is a representation of an appropriate Levy subgroup. I take this representation and I induce that up. So that's what I called S sub Z of the multi-segment A. And correspondingly, we had S sub Q of the multi-segment A, where instead we played the same game, but with our unique irreducible quotients attached to each multi-segment. So we had in both of these stories, the sort of punchline was that this S sub ZA came with a unique irreducible subrepresentation. And likewise, S sub QA, that came with a unique irreducible quotient. Well, of course, they both have a unique irreducible sub and a unique irreducible quotient. But in this particular case, there's sort of like for the SQ story, that has a special relationship with the QA, and same with this thing over here, which I'm going to expand upon in today's video. Did I need to do the recap? Maybe you just watched the one before and you're extremely bored. Maybe I should put timestamps to avoid that. Oh well. So here's how it goes. Remember, we also had these mysterious supercuspidal representations, right? So these were the ones that could not be accessed via induction. We can't view them as related to any representation parabolically induced from a Levy subgroup. So those are sort of mysterious. But now what we can do is attach to each of these, to each, say, multi-segment, I'm now going to attach, rather, well, there's two ways we can do it. So not necessarily to each, okay, there's ways that it works out either way, but I'm now going to sort of enhance each of my multi-segments. So not only are they going to be multi-segments in the traditional sense, but I'm also going to index each one of them with a supercuspidal representation, where now row I is a supercuspidal representation of an appropriate size. So, what's the best way for me to say this? So let's go back to our GL2 example, and I just had this as my multi-segment, right? So now what I'm going to do is, suppose that row is a supercuspidal representation. So we don't, what the hell is that? We don't know. But it's one of them, and it's for GLN K of the p-adic numbers. Then, in the same way as before, S of this now, marked multi-segment is going to be induced, this time not from the Borel, but rather what I'm going to do is take the appropriate Levy subgroup, which I'll explain in a second, and I'm going to take this representation. So I twist, so really I should write, oftentimes we drop it because the notation gets messy, but we're going to put these tensor products in here. And we induce this thing. So just to be clear, right? What is this representation that's being induced? Well, it's really a representation of the Levy subgroup, which has two diagonal blocks, GLNK, GLNK, where, if I have, say, a matrix, block diagonal matrix here, what I'm doing is I'm sending this to, the absolute value, just to be really explicit, absolute value to the -1/2 of the determinant of A, row A, tensored with the determinant B to the +1/2. I'm writing this in this case as a scalar out front of, these are linear operators, and on the if V is the underlying vector space of rho, this is a linear operator on this tensor product, right? This is and this, defines a representation on this tensor product. More generally, you can sort of, maybe you can imagine where I'm going. So of course, if I have delta sub rho AB, then the representation S sub rho, and here again, remember I have this notation at S sub Q. Oh, maybe I'll, yeah. No, I don't have that notation, but I can explain. This would be the same as S singleton delta sub rho Z and S sub Q singleton of delta. The reason being, well, you can see in a moment, but the point is, it's just we now choose the appropriate size parabolic. I was just too lazy to write out the formula, which is why I wanted to just give you that example. And now we take the corresponding twists. So again, I'm gonna drop the internal tensor product notation. And there we go. And perhaps one piece of notation I should introduce now, just to avoid, because I'm going to have to do it at some point anyways. So in the most general case, forget about multi-segments or anything. Suppose I just have any old representation, sigma 1 up to sigma r. The parabolic induction, I'm going to write this as a shorthand. I'm going to write this as just x's, as if it was a multiplication. And this is foreshadowing because it turns out it is just a kind of multiplication. So here's a fun thing. Maybe no one else thinks it's fun. I do. So when we say defined as, I'm like, A is defined to be the sum of blah, 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 or something, right? But sometimes in writing, you do a bunch of stuff and you want to define something afterwards. So then I write this notation the other way. And then for whatever reason, I think of it as, I call it phi dined, which is not defined backwards. But for some reason in my brain, I say, oh, this is phi dined as, this piece of notation, doing it the other way. Probably that won't ever make it into a paper because people will, I don't know, not like it, but this is a notation I like for myself. Okay. And great. So you can probably guess that just as before, we're going to do this one more time. And given a multi-segment where now I can have all sorts of different supercuspidals and whatnot attached to each of these segments, although our lives are made much easier. There's a whole bunch of ways we can split up this category so we can focus on one supercuspidal at a time. But for now, I'm just going to write things this way. We, just as before, this thing that we've created, this has a unique irreducible quotient, and which I'm going to call Q. And it's got a unique irreducible sub, which I will label as Z. And finally, as you can imagine, we're going to induce one more time. Of course, this P is not the same P as before. It's yet a larger parabolic. Again, just choose the appropriate size. And what are we going to do? Well, now that I've given you this notation, actually, I can make the definition much nicer. I'm going to define this, where now, remember, this multi-segment has a bunch of supercuspidals inside of it. This is going to be Z1 delta 1 rho 1 times Z delta 1 rho 2 times dot 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 Z delta R rho R. And likewise, definition of SQA. And again, these things still have unique irreducible quotients and unique irreducible subs. And the point is this: there's two ways we can frame this. I'm going to frame it one way in terms of the SQAs first. So major theorem. Major theorem. Well, we already know, we've already said that SQA. Ooh, there's something I need to tell you before the theorem. there's an ordering on these segments as well. So, uh, so suppose I have two supercuspitals and they are isomorphic. Rather, Actually, I realized my particular choice of notation has made something a little bit awkward. They don't quite have to be isomorphic. Um, Okay, but we can always choose. Uh, okay. I'm just gonna lie to you for a little bit, and we're gonna sort out the details later. So if I have uh for the same supercuspal representation, if I have two segments, call this AB and call this CD, delta 2, we say they're linked. We say they're linked if, I'm going to draw a picture in a second to make sense of this, but we say they're linked if the union delta is a multi-segment. Okay. So in terms of pictures, this looks something like this. If we actually think about the interval, you know, the intervals, like if this is, we imagine, of course, this is it's a discrete set of numbers. It's not a literal real interval, but if we imagine our two segments as being like this, right? So for instance, this could be -1, 0, and 1, and this could be 0, 1, 2, up to 3, right? So these are examples of linked segments. Here's an example of segments that aren't linked. So if we had this, and then 5, 6, 7, 8, 9, right? These are not linked. Here's another example of segments that are linked. We have -1, 0, 1, and 2. So we're allowed to have a jump by 1, right? That's the sort of the segments don't need to line up perfectly end to end. They do need to overlap, and we can have a jump of exactly 1, and we'll still say they're linked. When this particular case happens, we say that they're juxtaposed. I don't know if I'm even going to use that terminology. So you can see combinatorial things. Ooh, why are we making these definitions? There's sort of something combinatorial starting off, starting to show up. So we've got these multi-segments. We have this thing that says they're linked. And we also need, I should add, and we don't want, we're going to disallow the possibility that one of these multi-segments is contained or equal to the other. So they are not going to be linked in this case. So for example, if I had two segments that were exactly the same, -1, 0, 1, and -1, 0, 1, these are not linked. So they're allowed to overlap, but one cannot be completely contained within the other. That's the thing. And so we now say that delta 1 precedes delta 2. Again, I'm going to have my choice of supercuspal representation here. And maybe I'll fix my notational error in just a moment. So Delta 1 precedes delta 2 if, well, yes, if they are linked and, well, you can just sort of imagine it that, the minimum element, so, okay, maybe I'll write it as AB and CD, and A is, oh, but I said for arbitrary complex numbers. Yikes, I've really put pinned myself here into some awkward notation. But they have to differ by one. So yeah, okay. So I'll say it this way. If the real part of A, haha, everything's fine. My notation's fine. If the real part of A is less than, well, it certainly can't be equal to C in this case. But we'll say less than or equal to C. Yeah. So of course that's an example. Like if I were to scroll up, we would say that this this segment here precedes this segment. Okay. And one thing I want to say about the supercuspidals is that if rho is supercuspidal, then new rho is also supercuspidal. And it's possible. No, I'll just fix it in the next video. I'll fix it in the next video. So here's okay, so here's approximately the major theorem minus one or two small technical issues I don't want to fix quite yet. The major theorem is that, so not only does SQA have a unique irreducible quotient, the real important punchline is that and actually this means I lied to you in the last video as well. Let A be a multi-segment such that SQA such that if I is less than J, then delta I rho I does not precede delta J, rho J. So basically the larger segments go to the left and the smaller segments go to the right. Remember, this ordering affects where we place those tensor products in our induced representation. Then, under this condition, that's the whole reason why I said this condition. Then, and this applies to the version I said in the last video too, wasn't quite accurate because there are orderings that are decomposable. Then, SQA has a unique irreducible quotient. And this is the big kicker. This is the big punchline that we really care about. Given any irreducible, so I mean smooth irreducible representation of GLN QP, there exists a multi-segment A. So remember, that means it's some choices of, intervals of numbers differing by one, together with choices of supercuspidal representations, such that pi is isomorphic to QA. So that's the big punchline. I feel I went into maybe too much esoterica, and I hope I didn't lose too many people before this big kicker, because now we get to dive in and sort of dissect this. But yeah, the point is, this gives us a complete classification of the irreducible representations of GLN. Every single one of them shows up here. Given any irreducible representation of GLN, there exists a multisegment such that pi is isomorphic to this quotient determined by the multisegments. Moreover, A is unique up to reordering the segments such that they satisfy the does not precede condition. DNPC, I guess I should call it. So basically, we can parameterize. We now have an understanding of all representations of p-adic GLN purely, well, almost entirely in terms of just these collections of segments of complex numbers that differ by one, with the major caveat that so it depends on the segments and pending the construction of all the supercuspitals. So this mysterious black box that we don't know about. However, I don't want to say this isn't important. It is very important. But for example, for the purposes of the Langlands program, which we're secretly interested in, like these are the representations. So remember, there was one supercuspidal, and that's if we took the trivial representation on QP cross. So in this particular case, this very special supercuspidal, so if we restrict ourselves to the case of this, we get what are called the unramified representations. Actually, I need to be careful about what that means, because the word unramified means different things to different people. There's K unramified for the maximal compact. There's not so many of those. And then there's the Iwahori unramified, but we'll get to that. We'll get to that. Those are just nonsense words to you right now. So the point is, actually, most of the representations that sort of come up in nature that we care about, at least if you're an automorphic forms type of person, are this. So yes, to truly get all of the representations, we need the construction of supercuspitals. But it turns out that like the abundance of the like most natural ones to look at all just involve the trivial supercuspal representation, which what could be easier to understand than that. So in other words, really the case when we're just inducing characters from the Borel. Or then, you know, going on to take combinations of those for higher Levy subgroups. Okay. I think that was a lot. So yeah, maybe just yeah, just to say one more time, the big punchline of this is that all of our irreducible representations of GLN are completely parameterized by the combinatorial gadgets of these multisegments, and then also pending the existence of these supercuspitals. I will maybe drop for now the supercuspitals, and we will just focus on the case of these unramified representations. But I'll let you know now that in the next video, so in the next video, we're going to talk about operations, combinatorial operations on the multi-segments that actually tell us something about the structure of how these representations are related to each other. And basically, I think for simplicity, I'm going to drop the supercuspitals, even just as a notational convenience. But like literally in the next video, anywhere you see me write a delta, you can just replace a little supercuspital there, and everything will work out just the same. And in fact, in a future video, I'll perhaps show that we can, or at least discuss rather, the result that I mentioned we can have all these little different supercuspitals attached to these segments. And in fact, all of our representations decompose in a very nice way where you really just need to focus on one supercuspal representation at a time. So I think that's where we'll leave it for today. And I hope you're still with me. And I hope to see you in the next video.